Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. We are going through the I/O subsystems. We discussed the techniques corresponding to programmed I/O. We said in order to reduce the CPU time, the interrupt-driven I/O is a better technique. For the interrupt-driven I/O, we discussed two examples. One example for the case of SRC processor as given in your book. In the textbook example, the processor uses the memory mapped I/O. We considered a second example for processor FALCON-A. FALCON-A has been discussed in earlier lectures, and we just went through an interrupt-driven I/O program. We discussed the flowcharts and the corresponding assembly language program. We illustrated how could we utilize the interrupt service routine and how could we call the interrupt. For the interrupt mechanism, we discussed a very simple hardware interface which consisted of a Falcon processor having 2 pins connected with a corresponding D flip-flop. So therefore, whenever an interrupt request is initiated by software or through hardware, it is passed on to the FALCON-A processor. We assumed there is only one interrupt which is possible at a time. So the CPU handles the instructions at hand and then passes on an interrupt acknowledge to the D flip-flop and therefore on to the printer. We considered the Centronics interface as the example. I hope you remember that we had 3 registers. In each case, every register has 2 bytes. For the example, we considered example addresses 56, 58, and 60 decimal. The example for SRC as given in the textbook was for an input device. So the data was passed on from keyboard to the CPU under an interrupt. Now for the case of Falcon, we illustrated the use of an output device. So we said that the characters are to be printed onto a printer using a Centronics hardware interface. Now with the addresses as indicated, we could test the status, and if the printer is not busy, that means it's available for printing, the corresponding data would be passed on from CPU on to the printer. We would like to have the illustration for a simulator. This simulator we will call FALSIM. It is an application program which has been developed by Dr. Anjum and Mr. Muzammil. We have been talking about this particular simulator for different programs in our initial lectures. Today, we will go in a little bit more detail and illustrate the use of this simulator for a particular program which we have discussed in the last lecture. That is, a printer driven from the CPU under the control of an interrupt. FALSIM basically is an application program, and it has got 2 modules. The input file for this application program is an assembly program written for FALCON-A, that is, using the instruction set of FALCON-A. Just to remind you, you know that the words used for FALCON-A correspond to 2 bytes and big endian format is used. Now, the assembler is the first part of the program, application program, and then corresponding to the files generated by the assembler, the corresponding simulator would use these files as input. There are 2 passes in the assembler. In the first pass, we will generate a symbol table. The symbol table would correspond to the variables, labels, and data values corresponding to a given data structure. Now, if there is some error in the first pass, that would also be indicated in one of the window panes corresponding to the graphical user interface for this assembler. We are going to discuss the assembler and simulator in more detail. For the case of assembler, the corresponding graphical user interface is shown in the next slide. The FALCON-A assembler module has 2 passes, as we said, the first pass and the second pass. The first pass module takes an assembly file with an extension .ASMFA. ASM corresponds to assembly program and FA for this particular processor, Falcon. And the processes the file contents corresponding to this assembly file. It would create a symbol table which corresponds to the storage of all program variables, labels, and data values. If the first pass completes successfully, a symbol table is created as an output, which is used by the second pass module. Failures of the first pass are handled by the assembler using its exception handling mechanism. The second pass module sequentially processes the .asmfa file, which contains the instruction opcodes, register codes, and constants using the symbol table. It then produces a list file with an extension .lstfa, independent of successful or failed pass. If the second pass is successful, a binary file with .binaryfa extension is produced, which contains the machine code for the program corresponding to the assembly file. Now we would like to look at the features of the assembler, and we will illustrate that by using the window corresponding to the first module of the application, which we call the assembler. As already illustrated, the assembler would take the input as assembly file. That means it would have .asmfa, and as a result would generate the corresponding 2 files. One would be the list file, and the second one the binary files. Let us look at the different aspects of this assembler and how to use it in the next slide. In this slide, the select assembly file option enables the user to use a FALCON-A assembly file and open it for processing by the assembler. On the right corner here, you see there are assembler options. There are 2 options, a print instruction table and a print symbol table. If none of these two is selected, then correspondingly we will not get a print for the instruction table and the symbol table. If we select, as an example, print symbol table, this feature, if selected, would write the symbol table produced after the execution of the first pass of the assembler to a FALCON-A list file, and it would have an extension .lstfa. The symbol table includes variables, addresses, and labels with their respective values. The second option, print instruction table, if selected, writes the instruction for a FALCON-A as used in the program. The corresponding extension would be .lstfa. List file is exhibited in this part of the graphical user interface, or let us call this window pane. The list file feature gives a detailed insight of the FALCON-A listing file, which is produced as a result of the execution of the first and second pass. It shows the program counter value in hex and in decimal, as you just see in the first two columns, with the machine code generated in the third column. The line number and the source statement appears as it is available in the original source file. The lower part of the window pane contains the error log. One could just shift and get the corresponding size of the window pane changed. The error log corresponding to this window pane would inform the user about the errors and their respective details, which would occur in any of the two passes of the assembler. Now you will just see at the bottom a search option. In the case of the search option, you could highlight the corresponding strings in the program and then go through the match and see how many matches would be there. It would be indicated in this field. Now we could select two options, match as a whole or match any, or if we want lowercase or uppercase, or we have a case sensitivity, we could select a case sensitivity in this particular option. The start simulator feature, as indicated here, is run using the FALCON-A assembler's start simulator option. We could invoke the simulator from the assembler. If we want to exit, just we come out of this assembler. To invoke again the assembler, we just double click the icon for the Falcon. After looking into the different aspects of the assembler, we now know that after running the assembler, we get a binary file. This binary file would be utilized by the next module, which is the simulator, and we call it FALCON-A Simulator. The function of the simulator could be invoked, as we just have seen, from the assembler, or which is a button start simulator. Once we start the simulator, a new window would be opened. In this window corresponding to the simulator, one would be able to observe different features. One would be able to go step by step and execute the instructions through the program, one instruction at a time. Now, if you like, you could also specify a breakpoint and run the whole program from one breakpoint to another breakpoint. The simulator would also indicate the contents of different registers, and we know that the corresponding registers with placeholders R0 up to R15 would be indicated. Now, since Falcon is a non-memory mapped processor, we need a separate window for I/O. The I/O addresses would be different, so we could see the corresponding data available at these I/O addresses. Now we have two windows for the memory, so we could see the contents of different memory addresses. Let us look at the illustration of the simulator window in the next slide. This slide shows the graphical user interface for the FALCON-A simulator. The top left button here corresponds to load binary file, which allows the user to choose and open a FALCON-A binary file with the extension .binfa, which has been generated previously by the assembler. Now this area corresponds to the registers and the corresponding value. Now this area here, this window pane, corresponds to the instructions. It contains the value of the PC, here the address of an instruction. Then we have the instruction represented in hex. Note, this address and instruction here would both be in hex. Then correspondingly here we have the assembly language equivalent of this instruction, and then further on we have the RTL description which we have discussed previously, and then the type of instruction and corresponding opcode. This part of the simulator indicates the I/O ports. These ports are available for the user to enter output or input operation values and visualize the operation values whenever an I/O operation takes place in the program. The input value for an input operation is given by the user before an instruction is executed. The output values are visible in the I/O port area once the instruction has successfully been executed. Now these two parts correspond to the memory, and for any location in the memory shown here in the first column, we could visualize and see the corresponding contents here. Now these contents could be viewed before, during, and after the execution of the program. At the bottom here, the processor state is indicated. The two registers, the program counter and the instruction register, which points to the next instruction to be executed, indicate the processor state. You remember there are no flags provided in Falcon-A, so the contents of IR and PC would give us the state of the processor. Now we have a number of options here, a number of buttons with the help of which you could just process the simulation. Single step here corresponds to the execution of one instruction at a time. The next instruction is not executed unless the user does a single step again. By default, the instruction to be executed will be the one next in sequence. It changes if the user specifies a different value of the program counter and through the change PC. Like if you just change the corresponding contents here, you could have 3, 4, 2, 0 and just see the corresponding, this is invalid value for the PC given. We change it again, change PC, and it is 1, 1, 1. By default, the instruction to be executed will be the one next in sequence. It changes if the user specifies a different PC value using the change PC option, which is available here as a button. And instead of 0000, one could feed as an example 0002, and the program counter changes from 000 to 0002. Similarly, we have a number of other buttons here available, like here is execute. By choosing this button, the user is able to execute the instruction with the options of execution with or without breakpoints inserted in the program. In case of breakpoint insertion, the user has the option to choose from a list of valid breakpoint values as shown in the window. It also has the option to set a limit on the time for execution. This maximum execution time option restricts the program execution to a time frame specified by the user. It would help the simulator in exception handling. Here you just see, if we do not want any breakpoint, we click here, no breakpoint. And here is maximum execution time, which is indicated here 10 seconds. You could change this value, drag it to a value like 100 seconds here, or you could put a numeric value in this particular field. Similarly, we have a number of other buttons here, like change the register. We could change the contents of a particular register. As we said, the number of registers available for FALCON-A are 8 registers, each one corresponding to 16 bits, that is 2 bytes. Similarly, we could just change or display the memory corresponding to an address, change IO or display IO. This we'll see in the use of this simulator with the example which we are going to take up next. This material regarding the assembler and simulator, as I said, has been covered earlier. It might be a bit of review or repetition, but still it is worthwhile because it's a very important tool, and to illustrate in the later example the concept of interrupt and the source file for the case of a driver, which is a printer driver for this FALCON-A, we need to very clearly understand and make use of these tools. It is suggested that you take this tool from your course material and try it on your PC. Run it again and again, the assembler and the corresponding simulators for different programs. For the sake of illustration, we will discuss the example as we saw in the previous lecture for the case of a printer driver. Certain rules should be followed for the assembly file, which we call just the source file. The source file should have certain comments which would be good for proper documentation. Now each comment would start with a semicolon. So anything after the semicolon in the line would be treated as a comment and the assembler would ignore it. Similarly, each line would correspond to a carriage return. So at the end of the line, there would be a carriage return. Now there would be a number of directives to tell the assembler what to do. Now in hand assembly, we could just do that manually, but for the case of assembler, we just tell the assembler how to treat the source file. Now these directives could be, for example, .org. .org would correspond to the first address for the code. Actually, it could be placed anywhere in the program. Nevertheless, for our program, which we have as an example, we take .org0, which means that the first address, which is a 0 address, would correspond to the first instruction in the program. For this example, it is a jump instruction. Later on, you will see in the program, and this would be jump to a label which corresponds to a main. Now, instead of calculating the exact addresses, we have talked about the relocatable code. To make the code relocatable, we use labels. Now, any label would be followed by a colon, like main colon would correspond to an address. So, the user need not generate this address. This address would be generated by the assembler. Similarly, the directive .dw corresponds to define word. Now, we could define the corresponding number of bytes required for a particular variable. Now, there is an option of .db define byte. However, usually the addresses for FALCON-A would be aligned. That means all addresses would be divisible by 2, and usually we will not prefer to use .db. Then we have .sw, which is the constant or a variable defined with this directive .sw. Now, the end of the program would contain a directive .end, which would correspond to the last instruction for the case of a given program. Now, for this particular example, we will define the memory map and see the corresponding areas defining different parts of the program. That we will illustrate a bit later in the lecture. The memory map for FALCON-A example corresponding to the interrupt service routine is indicated. As we said, 0 address corresponds to the entry point. Address 2 contains the address of the interrupt service routine, and this would point to the beginning or the first address for interrupt service routine. Therefore, the ISR could be located anywhere in the memory. Then we have at address 4 corresponds to the data area from 4 up to 31. Now, the address for the printer driver, which initializes the printer, is given at 50. The main program for this example, which we just call the dummy calling program, is located at 32. Now, we have for this example the ISR address as 100 and the print buffer, which indicates the first address where the characters to be given to the printer or to be printed are located. So, an array, for example, of 80 characters would start from the address 1024. Now, the corresponding program is also indicated, and see that .org0 directive has been used as the first line in the program. Although the use of this line is optional, its use will make sure that FALSIM will start simulating by picking up the first instruction stored at address 0 of the memory. Address 0 is called the reset address of the processor. A jump within square brackets first instruction can be placed at address 0, so that control is transferred to the first executable statement of the main program. Thus, the label first serves as the identifier of the entry point in the source file. The .org directive can also be used anywhere in the source file to force code at a particular address in the memory. Address 2 in the memory is reserved for the pointer to the interrupt service routine. The .sw directive can be used to store the address of the first instruction in the ISR at this location. Addresses from 4 up to 125 can be used as addresses for data and pointer. Any address between 4 and 14 can be used in place of the displacement field in the load or store instructions. Just recall that the displacement field is just 5 bits in the instruction set for FALCON-A. However, the main program must start at address 126 or less. Otherwise, FALSIM will generate an error at the jump first instruction. This restriction is because of the fact that the immediate operand in the move immediate instruction must fit an 8-bit field in the instruction word. The main program should be followed by any subprogram or procedures. Each procedure should always be terminated by a return RET. The interrupt service routine, if any, should be placed after the procedures and should be terminated with iReturn instruction. The last line in the source file should be .end directive. Note that .equate EQU directive can be used anywhere in the source file to assign values to variables. It is the responsibility of the programmer to make sure that code does not overwrite data when the assembly process is performed, or vice versa. As an example, this can happen if care is not exercised during the use of .org directive in the source file. Now we are going to illustrate the use of FALSIM with the help of the previous example. The problem is as follows. We have a buffer and there are, as an example, 80 characters located arbitrarily in the memory, as an example, from 1024 onwards. The total number of characters are also defined. Now we just need to satisfy the initial conditions to set up the printer and have an appropriate handshaking between the printer and CPU. This was illustrated in the last lecture, and I hope you remember there were 3 parts of the program. Whenever a user invokes the corresponding print command, then the printer driver would be invoked. The printer driver would initialize the appropriate values and then it would invoke the interrupt service routine. The interrupt service routine would check the status of the printer, and if it is not busy, it would pass on the corresponding character to the buffer of the printer. We have 3 registers corresponding to the Centronics interface. So the data port is there, the control port and the status port is there. We will now go through this particular example written in assembly, which we discussed last time, and run it on our simulator in FALSIM. Let us go step by step through this simulator and visualize the contents of memory, the different registers, and the I/O ports for this particular example. Let us start the FALSIM, that is FALCON-A Simulator and Assembler, by double-clicking the icon FALSIM. Now we see the assembler window. Select one or two of the options. Let us select print instruction table and print symbol table, both in this example. Then we click on the select assembly file. Now on the desktop, the corresponding files are available. For our case, we have example-11-10, this file. We just open this file. Now, by opening this file, we get the corresponding window showing that the following files are generated successfully. As we said, just see, one of these files is a list file, the other one is a binary file, and we just see the corresponding addresses in hex and decimal, the instruction, the line number, and the source statement. We just put OK, and correspondingly we get the window for the list file. Had there been some error, this area would contain and report the corresponding errors to the user. If there is an error message, that would be highlighted, and by double clicking that error, we could correspondingly go to the original file, correct that particular instruction, and rerun the assembler. For this example, we do not have an error in the program, therefore both the list file and binary files are generated. Now we start the simulator by clicking the button Start Simulator. With this, we go to the simulator window. We need to select the load binary file. Now again here, the binary file which has been generated by the assembler is invoked. Note that the first instruction at address 0 is ready for execution. All the registers have been initialized to 0. The memory contains the address of the ISR, which in this case is 64, corresponding to a decimal 100 at location 2. The address of the printer driver is available at location 4, which is in this case 32 hex. In a real situation, these addresses will be determined at execution time by the operating system, and thus the ISR and the printer driver will be located in the memory by the operating system, and this is the concept of relocation. Subsequent memory locations contain constants defined in the program. Let us use the single step button. When we click it, the first instruction would be executed, which means jump to main. And you see here that the program counter jumps from 0 to 20. This address 20 hex is the address of the first instruction in the main program and corresponds to the label main. Although in a real situation, there will be many more instructions in the main program, those instructions are not present in this dummy calling program. The first useful instruction is shown next. It loads the address of the printer driver in R6 from the pointer area in the memory. The registers R5 and R7 are also set up for passing to the starting address of the print buffer and the number of bytes to be printed. Through the single step operation, the next instruction executes and takes the contents at memory location 4 to register 6, and just see that the contents of the register here for R6 is 32, which is the location of memory location 4. Similarly, the next two instructions place the contents corresponding to the two next memory locations in registers R5 and R7. This is required for passing the starting address of the printer buffer and the number of bytes to be printed. In our dummy program, we bring these values into these registers from the data area in the memory and then pass these values to the printer driver using these two registers. Clicking on the single step button twice executes these two instructions. The execution of the call instruction now simulates the event of a print request by the user. This transfers control to the printer driver. Thus, when the call R4, R6 instruction is single stepped, the program counter changes to 32 hex. Just here PC value is 32 hex for executing the first instruction in the printer driver. Now double click on memory location 000A, which is being used for holding the print busy flag. It is 0 before we change it. Let us enter a 1 and click the change memory word, which indicates that the previous print job is in progress. Now click again the single step and note that this value is brought from memory location 000A into register R1. This is register R1. Its value has changed to 1. Clicking single step again causes the jump not 0 R1, message instruction to be executed, and the control is passed to the message routine at address 46 hex, which in this example is a no-op instruction. Click again on the single step button. Note that when the return 4 instruction executes, the value in R4, which is 28 hex here, is brought to the PC. Click again on the single step button. Note that when the return R4 instruction executes, the value in R4 is brought into PC. This blue highlights the instruction corresponding to the value in R4. The blue highlight bar is placed on the next instruction after the call R4, R6 instruction in the main program. Now we double click the value of the PC, which is labeled in this case here. We change the value corresponding to the PC for call, which is 26 hex. So we come back to the call instruction. Now we change the memory location at address 000A to 0 instead of 1, and it is brought to R1 so that when the next jump not 0 R1 message instruction is executed, the branch will not be taken and control is transferred to the next instruction after this instruction. Let us take the program counter, change it to value 0 and restart with single step. Continue single stepping till the interrupt instruction and note the changes in different panes of the simulation window at each step. When the interrupt instruction executes, the program counter changes to 64 as indicated here in processor status, which is the address of the first instruction in the ISR. So the control is given to ISR. Clicking single step executes this instruction and loads the address of the temp label, which is a temporary memory area for storing the environment. Just see here. The 5 store instructions in the ISR save the CPU environment, which corresponds to the working registers before the ISR changes them. In the same way, if we go through single step through the ISR while noting the effect on various registers, memory locations, and I/O ports till iReturn instruction is executed. This will pass control back to the printer driver by changing the program counter to the address of the jump finish instruction, which is the next instruction after the interrupt. Double click on the value of the PC. Change it to the point of the interrupt instruction and click single step to execute it again. Continue to the step till in R1 status port instruction is ready for execution. Now change the I/O port at this address, which is 3A hex, and see the contents. It would bring the status port and R1 would contain 0080. Single stepping twice and notice that the control is transferred to the move immediate R7 instruction, which contains tetra F instruction, and this corresponds to -1 in register R1. Now we have gone through the details of using the assembler and the simulator for our example processor FALCON-A. Now a practice would give you a better idea into the operation of the assembler and the corresponding simulator. Through single stepping, we have just noticed how the memory locations change and the contents of the corresponding registers change. We had the option of changing the contents of program counter, any of the registers, any of the memory locations, and through illustrating that we could simulate the printer busy status by changing the contents of the relevant address from 0 to 1. 1 simulates printer busy and 0 simulates the printer is available for printing. And at the end, in register R7, we checked for a value -1, which corresponds to the done flag. That means all the characters have been outputted and printed. Now, the assembler corresponding to any particular processor would be available as a tool from the manufacturer. As an architect of the FALCON-A, Dr. Anjum has developed this tool for you, and you need to practice this to get more insight into the operation of the assembler and the corresponding simulator. You could take more examples and go through the simulator step by step to get more insight into the operation of assembler and simulator. That's all for today. Till next time, Allah Hafiz.